All right. So second to last section we're going to look at in chapter 1.5. It's on quadratic functions and transformations. Transformations are something we're going to study like 6 or 7 different times. Every single function that we study throughout the year, one of the things we do with them is learn how to transform them, meaning like shifting up and down, shifting left and right, stretching, reflecting, things like that. And there's like maybe 7 different big categories of functions that we're going to study each chapter that we do, and transformations will be a part of every one of those. So we're going to focus on quadratics today. So in general, a quadratic function has the form ax squared plus bx plus c, where, and I think I had something like that on the board yesterday. Can someone basically tell me what that says about the a, the b, and the c? Yep.
A, B, and C are all in set of real numbers.
Yep, a, b, and c are all in the set of real numbers. And the only restriction is a can't be 0. Why can't a be 0 in a quadratic? What would happen if a was 0? Courtney?
It would make x equal 0 and
Well, it wouldn't necessarily make x equal to 0. It would make a 0. But what would that do to your expression? Yeah, Jack?
It would make it linear.
It would make it linear. If a was 0, it would effectively wipe out the quadratic term. Now you have bx plus c. That's a linear equation. Okay. So other than a equaling 0, a can be anything other than that, and b and c can be any real number. B and c could be 0, that's fine, but not a. All right, so let's graph on the calculator y equals x squared. And let's look at the difference between plugging in x and plugging in negative x. Okay. So what I'm going to do is I'm going to use parentheses because anytime you want to plug in a negative, you should always put it in parentheses. So let's do x. We're going to square it. And that pencil sharpener will probably work better than this electric one. You can use that one if you want, but that one will work better. And let's do negative x and square it. All right, and let's look at the difference. So type in the 2 things just like I did. And then we're going to do zoom 6. Yep. Okay, so there's the original. That's the x squared. And here's the other one, the negative x squared. They look the same. But something actually happened there. Does anybody know what this negative actually did? Yeah?
It inverted it.
What do you mean inverted it?
It flipped around. Oh.
Yeah, it flipped it. Can you be more specific with how it flipped it?
Horizontally.
Yeah, you could say it did a horizontal reflection over, yep.
The x-axis.
Nope, not, well, over the x-axis would be a vertical reflection. If you flipped it top to bottom, that's a reflection over the x-axis. But this one reflected over the, yeah, so it's kind of hard to see because a regular parabola is already symmetrical over the y-axis. So if you reflect it over the y-axis, effectively you don't notice anything. But that's really what that negative did. So generally when you see a negative inside, like right next to your x variable, that will take your function and reflect it. So in this case, the y-axis is a line of symmetry. In this particular problem, the lowest point of the parabola, that's called the vertex. But the vertex can also be the highest point if the parabola is reflected So it opens down instead of opening up. So what we're going to want to be able to figure out is if we shift the parabola, the vertex is normally at the origin, but if we do a transformation to it, that vertex could move. We want to figure out what the new vertex is going to be if we move the parabola. So that's one thing we're going to look at today. All right, so when you're trying to figure out the different transformations, sometimes it's helpful to just take one of the letters in the problem, okay, like the A, and just start changing it to different values and see what does it do to the graph. So let's try typing in like y equals x squared, 1/3 x squared, and 2x squared. And just kind of see what happens. All right, so type in the original. I don't have any negative with the x, so technically I don't need parentheses around the x. That's okay. 1/3 x squared. A couple ways you can type in fractions. I usually just do it like this. 1/3 x squared. Add 2x squared. All right, so we're going to do zoom 6. And then we're going to look at what each one of those looks like and see if we can tell what changing that number in front is doing to the picture. Okay, so there's your original. There's the second one. And the third one. So anybody think they can explain what the effect is when you change the A value? Yeah. Roger.
Vertically stretches or squishes it.
Yep, exactly. Well, sometimes people describe it horizontally, but they usually describe this one vertically, either as a vertical stretch or compression. So pretend like it's glued down at the origin. If you were to take the sides and vertically stretch it, okay, like pull up on it, it would get skinnier. Think if you had like Play-Doh, right? It's like glued down and you pull up on it, it gets long and it gets skinnier. If you were to take and squish it, like vertically, try to compress it, it would start to spread out sideways. And that's what's happening here. So there's basically two cases. If A is greater than 1, that causes your graph to stretch vertically. I'm just going to say that a little differently. If the A value is between 0 and 1, then the graph is going to shrink vertically. And in this case, it pretty much makes sense. The bigger number causes it to stretch and get bigger. The smaller number causes it to shrink and compress down and get small. Generally, whenever you're doing something that affects a graph vertically, it's more common sense. Okay, what you see happening with the numbers is what actually happens in the picture. When we start doing things like left and right, it doesn't make as much common sense. It's usually backwards. Okay, but for things that are vertical, bigger numbers will stretch it bigger. Small numbers like decimals will shrink it down smaller. Okay, any question on that? Yeah?
I just had a question about my calculator.
Mhm.
For some reason, it's got like all these blue shades.
All the blue shades?
Yeah.
So that's because somebody turned on the shading. So if you go to your y equals and press the left arrow and highlight the color shading that you see, and then hit enter, instead of having it on a line that looks like this, they probably have it on a little triangle that looks something like that.
Yeah.
So So what you want to do is take it from being on that triangle thing and then put it back so it looks like there's actually a thin line and then there's like a thick line. So I would put it on the thick one. Press OK. And then when you hit graph, it'll be fine.
Okay, thank you.
Yep. No problem. All right, now let's do the same thing again, but let's take one more step and see what happens when we make a negative number. Now, this is a little different than where we put the negative before. I'm not putting the negative inside parentheses with the x. I'm putting the negative in front of the whole thing. Okay. So there's a difference between something like this and something like this. One of them has a negative in front. The other one has a negative inside the parentheses, right, attached to the x variable. They're both parabolas, but they're different. They're a little different. So let's see what happens when you put a negative in front. Okay, so let's do negative x squared. Let's do negative 1/3. That's how I type it, x squared. And negative 2x squared. And remember, the negative is the button below the 3. Okay, so let's type all these in and see how these parabolas compare to the 3 that we just drew. Remember, they all have a negative in front. What did that negative in front cause to happen in the graph?
Flips on one side.
Yeah, it did what, Wayne?
It flips on the x-axis.
Yeah, this did a reflection over the x-axis. Negatives always cause a reflection. It can either be over the x-axis if it's in front of the function, or it can be over the y-axis if it's inside the function with the variable. So the negative causes the graph to open downward. You can call that a vertical reflection over the x-axis, or you could just say reflect over x-axis. Okay, so one thing that we'll do a lot of is I'll give you a function. I'll give you a function that's been transformed, and I want you to tell me how it's been transformed. Okay, so the first thing is let's see if we can identify how many transformations are occurring to turn this into that. Anyone think they know how many transformations are happening? Yep. There are 2. Yep. So there are 2 transformations. When you describe transformations, you do have to describe them in a certain order. If you don't, it's like doing PEMDAS in the wrong order. You'll get a different answer. So we're going to learn what that order is a little bit more like today, and then we'll study it a lot more throughout the year. But let's start with the 5. So we'll start close to the x, and we'll work our way out. What is that 5 in front of the x squared doing? That was the first transformation we talked about.
It's compressing it in small.
So let's go back and look at, where did I write that? So in this case, A is 5.
Oh, it's
Stretch, yeah. So we would say that that 5 is causing it's a vertical stretch, and then you have to tell me how much, by a factor of 5. So what that means is if you had a bunch of coordinates on this graph, if you wanted to stretch it by a factor of 5, you would take all the y values and multiply them by 5. You wouldn't do anything to your x's. And that would make all the y's 5 times as big, and it it would stretch it 5 times as much. Okay, so that's the first one, vertical stretch by a factor of 5. Now, how about that negative in front? What's that doing? Yep.
Vertical reflection over the x-axis.
Yeah, so we could say that that's reflecting. Reflect over x-axis. So that's a vertical reflection. And that's what I'm looking for when it says, how does this graph compare to that graph? Exactly like that. Questions on that? Yeah.
I'm just a little bit confused. Vertical, like you say vertical stretch, and it makes me think it's getting bigger. But then when I graph it on here, it's getting smaller.
So a vertical stretch would be something like, put that up there. It's not going to let me, it's locking in the aspect ratio. But a vertical stretch would basically take something like that, and it would elongate it. So it would look more like that. That's a vertical stretch. A vertical compression, let me try it one more time, would take something like that. It's not letting me do what I wanted to. But a vertical compression would take a graph like that, and it would look more like that. That's compressing it. So when you compress it, it kind of widens out. Does that make sense?
Yeah.
So we usually describe that transformation vertically. The bigger you make the number, the more of a stretch you're going to get. So like if you do, let's just say x squared, and then you do 6x squared. Okay, that's going to stretch it out vertically 6 times as much, and it's going to get very tall and skinny. So because it's been stretched vertically. Now if you do something like 0.6, okay, just put in 0.6. What that's going to do is, because now you've put in a number less than 1, that red one is going to squish down and it's going to look wider. So it's going to be on the outside of the blue one. Because it got a little bit wider because it squished vertically. Okay. We'll talk more about the order you have to describe transformations in a little later. All right, let's look at this one. So this is adding or subtracting a number on the end of a function. Does anyone have a guess what a +2 on the end is going to do? Yeah? Shifted to the left, how many?
2.
Shifted to the left 2? Okay. Anybody have another guess what that +2 might do? Yep.
Shift it up 2.
Shift it up 2? All right. Thank you. Let's take a look at it and see what happens. So we've got x squared, and let's type in x squared plus 2. So there's the original. We shifted it up 2. Yep. So to get y equals x squared plus 2 from y equals x squared, shift up 2. Okay, so the original one, that's called the parent function, y equals x squared. It's the simplest quadratic that you can have. Everything else comes from that one. How about this one? To get y equals x squared minus 3 from the parent function, how do you think you would get x squared minus 3? Yeah, cool. Yep, you would shift it down. So again, vertical types of transformations usually make common sense. Positive is up, negative is down. So putting a -3 on the end of your function, shift down 3. And we're going to learn later on that it doesn't matter what kind of function you have. If you had a square root function and you do a -3, that would shift the square root down 3. If you had a trig function and you put a -3 on the end, that would shift the trig function down 3. So it doesn't, once you learn transformations, they apply to every function that we're going to study all year. Okay, so vertical shifts. Vertical shifts are what we call rigid motion transformation. They don't stretch the graph or distort it in any way. And to figure out which way the graph is going to move, look at the number that you've added on the end of the function. If it's greater than 0, it's going to shift up. If it's less than 0, it's going to shift down. Now I put absolute value of k units because if you put like a -3, don't say that it shifts down -3. Down is the negative. So it either is up 3, down 3. But it's always, the number itself is always positive. Any question on vertical shifts? Yeah. Yeah, just sign out for me. Okay, so next thing we're going to look at still has to do with adding or subtracting, but it's a little different. It's adding or subtracting, but it's inside the function. It's not on the end of the function. Okay, so it's adding or subtracting something right on the x. What do you think a -3 is going to do? Have a guess what it might do? Yeah?
Shift it to the right.
Shift it to the right. Yeah. Anyone else have another guess what it might do? About Nick?
Also right.
You think right? So people are thinking horizontal, it seems. It is going to do something horizontal. Let's try it. So let's type in, let's just do x squared and then x minus 3 squared. So x squared, x minus 3 squared. And you might think that it would go to the left because it's a minus. Negative numbers go to the left, but it doesn't. Horizontal transformations are usually backwards from what you would expect. All right. So x minus 3 shifts it right 3. Okay, so to get y equals x minus 3 squared from y equals x squared, shift right 3. Okay, I'm not going to write the other one. I'm just going to ask you guys, how do you think you'd get y equals x plus 2 squared? Oh, Amaya, what do you think?
Shift it left to.
Yep, you would shift left 2. So these are examples of horizontal shifts. Again, rigid motion doesn't do any kind of stretching or distorting. But it's backwards from what you would think like on a number line in terms of what the plus and what the minus do. So what I always do is I think of it as, I always try to put it in terms of x minus something. So like if I had a problem like this, x plus 2 squared, I think of it as y equals x minus -2 squared. Okay? If you think of it as x minus something all the time, then what you can do is look at what's after the minus sign. If what's after the minus sign is a positive number, it will go to the right. Right, so if you had something like y equals x minus 4 squared, it has a minus. Look at the number that comes after the minus sign, not the minus sign itself, what comes after it. That's a 4. That's going to shift it to the right 4 units. If you have something like x plus 2 squared, think of it as x minus -2. Look at the number that comes after the minus sign. It's a -2. -2 is going to go to the left 2 units. Okay, so there's different ways you can think about it, but somehow you've got to remember when you see the top case, it's going to shift it to the left 2 units. And when you see this bottom case, it's going to shift it to the right 4 units. Okay, any question on that? So that together with the H represents shifting left and right. K represents shifting up and down. H and K will give you the new coordinates of the vertex. Those are the only 2 things you need to know to figure out what the new vertex is going to be. What is the number after the minus sign? And what's the number that you added or subtracted from on the end of it? Now remember, the number at the end, it's not backwards. If it's +3 on the end, it's up 3. If it's -2, it's down 2. So that one, you don't have to do anything funny. Okay, and the line of symmetry. If you shift the parabola left or right, that will affect the line of symmetry. How come shifting up or down wouldn't affect the line of symmetry? Yeah.
Because you're not shifting left or right, so the y coordinates are, and the x coordinate is the same.
Can you say that again for me?
Could you repeat the question?
So how come shifting up and down doesn't affect the line of symmetry in a parabola?
The x coordinate is the same, so.
So yeah, if you shift up and down, yeah, the x coordinates stay the same and the line of symmetry is vertical. If you have something that's vertical for your line of symmetry, and you take your graph and you shift it along that line of symmetry, up or down, it doesn't affect the line of symmetry at all because the x values are staying the same. Okay? So the line of symmetry is only affected when you move things left or right. And what letter controls left and right? That's the H. All right, so let's look at an example and see if we can figure out the new line of symmetry and the new vertex when we do a transformation. Okay, so let's look at this one. So it's y equals x plus 2 squared minus 3. First they want the vertex, and then they want the line of symmetry. Remember, the vertex is h comma k. H is the number that's after the minus sign, and k is whatever's on the end. Okay, so just be careful with this one. What do you think the new vertex would be for that equation?
Two comma
So the -3 is good. Which way is that 2 going to cause the graph to move? To the
Left.
to the left. So if your vertex was at 0, 0, and it went left 2 and down 3, what would be the coordinate that's left 2 and down 3 from the origin?
-2.
-2 comma what?
Negative.
Yep. So that's the vertex. Left 2, down 3. And what about my line of symmetry? How about Lizzie? What would my line of symmetry be?
-2.
And how would you write the whole equation for it? You want to help her out? How do you write the equation? How does the equation for the line of symmetry for any parabola start? Yeah? X equals. Because it's a vertical. And then the line of symmetry would normally be x equals 0, which is the y-axis. But you've shifted left 2. So now the line of symmetry is also shifted left 2. How about this down 3? What effect does that have on the line of symmetry? It doesn't have any effect. Yep. Doesn't affect it at all. All right, so let's look at another one. And I'm going to start to talk about the order that we need to do transformations in. If you're not sure why the order matters, think of a problem with PEMDAS. Take a number, again, in your head, multiply it by 5 and add 4. And then do it the other way around. Add 4 and multiply by 5. Will you get the same answer for every possible number you could try? Megan, what do you think? No. Maybe you could find one number that it would work for or something. But in general, no. If you plug in like the number 2, multiply by 5 and add 4, well, that's 14. If you add 4 and multiply by 5, that's 6 times 5, that's 30. So it doesn't come out the same. So the order on the right is generally the order that we're going to follow. In this section, we don't do any horizontal stretching or shrinking. If you were going to do horizontal stretching or shrinking, it would come in right between steps 1 and 2. We will eventually, but these are the only transformations we're going to look at for parabolas. Horizontal shifting. We'll skip horizontal stretching or shrinking. Vertical stretch or shrink. Then any reflections in the x-axis. And then the very last thing is always a vertical shift. Okay. If you don't have a specific transformation, skip it. If you have it in the problem, write it down. All right. Well, let's go through and see what we have in this one. All right. Kaylee, how many transformations are happening in this problem, 5x plus 4, to turn it into, to change it from x squared to 5x squared plus 4? Yep, there are 2. Ryan, do I have a horizontal shift in this problem?
Yes.
Okay, tell me what number is the horizontal shift.
4.
Let's go back and look at horizontal shift. There we go. So look at what the pattern looks like for a horizontal shift.
I was at 5.
And now let's go back here and look at this one. So you think the 5 is a horizontal shift? Okay. Horizontal shift is when you add or subtract a number to the x value inside the parentheses. Are we adding or subtracting a number to this x value inside parentheses? Well, voices. No. There is no horizontal shift in this problem. No horizontal shift. Horizontal shift would be something like this. Now you have a horizontal shift of 3 units to the right. 3 units to the right. All right, let's go to the next one. Vertical stretch or shrink. Maddie, do I have a vertical stretch or shrink in this problem? Yes. Okay. What number is the vertical stretch or shrink? Okay. So let's go back. Look at the vertical stretch. So vertical stretch is when there is a number, we called it A, in front of x. So it's the 5. Right? So in this case, we have a vertical stretch. There's a 5. Ben, could you tell me how to describe that vertical stretch? We just say by a factor of 5. Yeah. So factor implies that you're multiplying rather than like shifting. So vertical stretch by factor of 5. Okay. Reflection in the x-axis. How about Cecilia? Do we have a reflection in the x-axis?
No.
No. If we had a reflection in either the x or the y, we would either have a negative in parentheses with the x, or we would have a negative in front of the entire function. So no, we don't have any reflection. So now the fourth one, vertical shift. Bella, do we have a vertical shift?
Yeah, that's the 4.
That's the +4. So adding or subtracting a number on the end, vertical shift. Can you tell me which way it's going to move?
Up 4.
Yep. So let's say shift up 4. You don't have to say vertical shift. When you say the word up, I know up is vertical. You have to tell me the direction and how much. If you just said shift up, no, that's not good enough. And if you just said shift 4, no. Shift up 4. All right. Let's try this one. So it's -3, and then in parentheses, x minus 1 squared plus 4. Cami, looking at this one, how many transformations do you think we're going to have to describe there? How many? 3? No, not 3. I can see why you might say 3, but it's not 3. Anyone have another guess how many? Yeah?
Maybe 4.
There are 4, yes. Yep. The 1, the 3, the negative in front of the 3, and the 4 are all going to do something different. So we got every transformation in this problem. Okay, let's start with the first one. Since we have all of them, you know there's a horizontal shift. Jack, can you describe the horizontal shift for me? I'm sorry, Jack. Yeah. Yes.
The horizontal shift
Hmm?
is 1 unit to the right.
We're going to shift 1 unit to the right. Yep. Okay, that takes care of the -1. Well, vertical stretch, that has to be the next one. Clover, how would you describe the vertical stretch? So start out with vertical stretch.
The vertical stretch stretch
Mhm.
by a factor of
I'm going to help her finish that. Vertical stretch by a factor of, yep, 3. Yes. Vertical stretch by factor of 3. Okay, how about, Courtney, what would be our third transformation? Yep, a reflection. Can you be more specific? Yep, that's what we call a vertical reflection. When it's in front, that's a reflection over the x-axis. And the fourth thing is the +4, which is a shift which way? Yeah. Yep. So anytime you see adding or subtracting in the problem, that's a shift. Anytime you see multiplying, that's a stretch. Okay. Trying to scroll over here. Guess I'm not going to do that now. Okay. All right. So, all the examples we've done so far have been in what we call standard form. Okay. If you have something that's not in standard form, well, it makes it a lot harder to figure out the transformations. So before we can describe the transformations, we have to get it into standard form. Okay. And what I mean by standard form is just like we did on the last problem. Let me scroll down. Okay, like that. If somebody FOILed all this out and combined like terms, that would make it a lot harder to figure out the transformations. So essentially what we have to do, if somebody did FOIL this out by squaring it, distributing the -3, and then adding 4, we have to undo all that and make it back like that. Okay? And the way that we do that is completing the square. So completing the square is something you would have done in algebra, maybe 1 or 2. I'll go through how to do it. Not really teaching a whole lesson about it because it's something we need to know in pre-calc. So 3x squared plus 12x minus 18. That's like a quadratic that somebody's FOILed everything out. I can't tell what the transformations are. I can't tell anything. I need to get it back looking like this. A number, parentheses, something squared, and then something added on the end. Not like that. Okay, so I'm going to show you how to complete the square on this one, and I'll make some notes as I kind of go through it. Okay. So anything that you don't remember that I'm kind of doing here, I would write down if you're not sure how to complete the square. If you already know how to do it, then there's probably not a lot you need to write down. So the first step when you're completing the square is the number in front of x squared has to be, well, a couple things. It has to be a 1. So we gotta work on that because we don't have a 1. And the other thing we usually like to do is start by putting the constant on the other side. Okay, so those are the two things that we generally do first. Right? I'm going to start by putting the constant on the other side. Okay, so let's start with that. All right, so we're going to have 3x squared, and think of like we're going to set it equal to 0. Okay, that's how we're going to put something on the other side. So there's the original problem. Now let's take the 18 and put that on the other side. Any questions on the first step of moving the constant to the other side? That's step 1. Step 2. You need to make sure that the number in front of x squared is a 1. If it's not a 1, you have to factor out whatever you need to factor out to make it 1. What do I need to factor out on the right-hand side to make x squared have a 1? Yep.
3.
I'm going to factor out a 3. Sometimes you don't need to do that step. If there wasn't a number in front of x squared, I wouldn't need to be doing the step I'm doing right now. Okay? But there is a number in front of it, so factor it out. If you're really lucky, the coefficient of the x term will be a multiple of what you factor out, then you don't have any fractions. So x squared, and what's going to come after that? Yep, 4x. Okay. Now, the next step is this is where the magic of completing the square happens. You've got to find some number that you can add to both sides. That's essentially going to make this part over here factor into two things that are the same, like x plus 4, x plus 4, x minus 2, x minus 2. It's got to factor into two things that are exactly the same, or basically something raised to the second power, something times itself. That's how we're going to get that exponent of 2. Does anybody remember what you have to do to find the number to add to both sides? And it has something to do with that. Okay, so the first thing you have to do with that number is take half of it. And then there's one more thing you have to do. And a hint is it has to do with the name of this whole process.
Complete the square.
You're going to take half that number, and then you're going to
Complete the square.
square it.
No.
So you're going to take half that number and square it. And that's what you need to add to both sides. That's the whole trick to completing the square. So you're going to have to add something here. And as long as you add the same thing on both sides, you've still kept the equation balanced, which is very important. You got to keep it balanced. So what's half of 4? Yeah? 2. And what do you get when you square it? 4. So take half and square it. The number in front of x. Now, you added something on the right. It's unbalanced now. You need to add something on the left to keep it balanced. What would you add on the left to keep it balanced? Yep?
Would you also add 4 on the left?
No. I know why you said that, though. That makes a lot of sense why you said what you said. But if you add 4 on the left, it will not balance it. Yeah?
Would it be 12?
It would be 12. Because you didn't really add 4. You added 12 when you distribute that 3 to it. So to keep everything balanced, add 12. That's the part that catches people sometimes. All right, now the rest is pretty easy. So we've got 30 equals 3. And how does x squared plus 4x plus 4 factor? It factors into something times something, and they're both the same.
X plus 2.
X plus 2, x plus 2. There's your horizontal transformation. Okay. There's your vertical stretch. And now, the last step is put the 30 back on the other side and set it and make it back equal to y. There's your vertical shift, down 30. Okay, so looking at the original problem, I had no idea that it was shifted down 30. I can't tell that at all. I can't tell that it was shifted left 2 units either. I could kind of tell the vertical stretch. That I could tell, just by looking at the number in front of x squared. All right. But now if you were going to describe the transformations, I'm not going to write them, but there would be 3. First one would be shift left 2. vertical stretch by a factor of 3, shift down 30. Those are your transformations. Okay, we've already done describing them. I think for this problem, the harder part was remembering how to complete the square. Okay, so quick overview. Step 1, constant on the other side. Step 2, factor out whatever you need to make the x squared have a 1 in front of it. Okay. Step 3, this is like the magic step that completes the square. Take half of the number in front of x, square it, and add that to both sides. Be careful if you factored a number out, because whatever you add is multiplied by that number you factored out. Simplify the left-hand side. If you added the proper number, this should factor very nicely. It could be x plus a number and then x plus a number, or x minus a number and x minus a number. But it has to be two things that are the same. It can't be x plus 2 times x plus 3. That wouldn't be to the second power. Okay, so always will factor into two things that are the same, and then put everything back on one side of the equation, and now you've completed the square. If you want to check it, you could graph that in y1, graph the original problem in y2, and they should look identical. If they don't look identical, then you made a mistake completing the square. All right, any questions on that? Now, you might sometimes, if you have to list the transformations, then you need to complete the square, because I don't know how you're going to look at that and know that it shifted down 30 without doing all those steps out. But if all they asked you for was the vertex, you can get the vertex from this. Even though it's a lot easier to get the vertex here. -2, -30. Okay, I can see it. There's a shortcut you can use to get the vertex here. And I'm going to show you what that shortcut is. The 3, 12, and the -18. Those are the letters A, B, and C. 3, 12, -18. As long as you know the A, the B, and the C, you can find the vertex. It's not really a formula I use a lot, because for me that's just something else I'd have to remember. I would probably just complete the square and figure out the vertex that way. But if you really just want to try to figure out the vertex and you don't want to complete the square, you can use this formula. Let's try it on this one and see if it works. So I know the vertex is left 2, down 30. Let's try the formula and see if it works. So -b, it's -12, divided by double A. So A is 3, double it is 6. Okay. And the next part is C, -18, minus B squared. Okay. What's B squared in this case? 144. Divided by 4A. What's 4 times A? 12. Okay. What's -12 divided by 6? There's your -2. What's 144 divided by 12? I'm sorry, what -144 divided by 12? Okay.
-12.
-12. And what's -18 minus 12? -30. So you can get the vertex using that formula. Again, I just would probably complete the square because I don't remember that formula off the top of my head. And same thing with line of symmetry. The line of symmetry is always just the first number of the vertex. It's the shift left or right. Okay, so last thing we'll look at with a quadratic is how many times a quadratic can cross the x-axis. What's the shape of a quadratic? What do we call that when you draw it? Yeah. It's a parabola. How many times can a parabola, what's one situation you could have if you drew a parabola in terms of how many times it crosses the x-axis? Yeah. Yep, it could cross twice. Whether it opens up or down, it could do something like that, cross twice. What else could it do? Yeah?
It could cross once if the vertex is on both sides.
Yeah, if the vertex is right on it, it could basically just come down, touch it, go back up. It could cross once. Yeah?
It could never cross.
It could never cross. Whether it crosses once, twice, or not at all, you can figure out just by looking at the numbers A, B, and C. You don't have to complete the square to do this. Okay. What's the y value anywhere along the x-axis? Yep.
0.
0. So that's why this is called the zeros of a function. The zeros of a function are basically a number that you can plug in that gives you an answer of 0. What does that mean? It's where the graph would cross the x-axis. Quadratics can have 3 different cases. They either don't cross at all, they cross once, or they cross twice. All you need to do to figure out which one of those 3 cases it is know what's under that gray screen, which I want to show you somehow. Okay, well, we'll figure it out. Does anybody recognize this b, that's b squared minus 4ac? Make sure you copy the 2. We got kind of caught up. Where do you see b squared minus 4ac?
It's in the quadratic formula under the square root.
Right, it's exactly, it's the radicand in the quadratic formula. If b squared minus 4ac, I think I got it now. B squared minus 4ac. If that value comes out negative, you will automatically know that your quadratic never crosses the x-axis. If b squared minus 4ac comes out to 0, it would be the case where it comes down, touches the axis, and goes back up. If b squared minus 4ac comes out positive, it would be that case. Now, if you want to know where it crosses the x-axis, b squared minus 4ac doesn't tell you that. If you want to know exactly where it crosses the x-axis, then you got to do the whole quadratic formula out. But if you just want to know how many times it will cross the axis, do this calculation, and the result will tell you. All right, so that is section 1.5. Okay, so the homework, again, there's lots of questions like in the section. It might go up to like 70 or something questions, so I just try to, I usually skip around. The homework is anywhere between 15 questions usually to 18 questions. I think this one's about 16 questions. Right, so we will go over that tomorrow. Normally tomorrow would have been a test day, but we'll hold off on the first test until the next academic week. Okay, so tomorrow will be section 1.6.